Hello again, AP Physics students. In today's lesson, we're going to wrap up our examination of all of these objects that have continuous charge distributions on them. And this time around, we're going to look at what's going on with a uniformly charged disk, and we're going to figure out the electric potential on an axis that passes through the center of the disk. So let's set the problem up. So we have a disk that has a radius of capital R. It has an area of A. It has a total charge of capital Q, and we're going to say it's positive. And it has a uniform surface charge density of sigma. So we're going to use the surface charge density instead of the linear charge density because this time around our object actually has area. This disk is centered on the origin and it lies in the XY plane. And we want to determine the electric potential at a point P that lies a fixed distance Z from the center of the disk along the Z axis. We're going to go through a series of steps to set this all up. So the way we deal with the disk is we're going to take the disk and we're going to break it into an infinite number of small little rings. Now, if we wanted to visualize what this would look like, we can just draw a few of them. So I have like an outer ring that's red in color. Again, this would have like an infinitely small thickness to it. Then I have another ring that's blue in color, infinitely small thickness. One that's green in color, infinitely small thickness. Then purple, and then yellow. And I only showed 5 of them here, but technically we're breaking the disk into like an infinite number of these little tiny rings. We're just going to look at one of the rings. So I don't want to look at the one. I don't want to look at the ring on the very far or the outside, nor do I want to look at the ring that's at the very center. So I'll take the blue one because it's kind of at an in-between state. So we're going to say delta A or dA is the area of one of these rings. Delta C would be, or DC would be the circumference of one of these rings. And the inner circumference and the outer circumference of the ring is going to be the same because the thickness of the ring, again, is like infinitely small. And speaking of that thickness, we're going to use delta R or dr to represent the infinitely small thickness of one of these little tiny rings. So we label on the picture, the ring I have in blue has an area of delta A. It has a circumference of delta C, and it has a thickness of delta R. Or if we write it in the calculus notation, it would be an area of dA, circumference dC, and it would have a thickness that's dr. And the other variable we're going to introduce here is we're going to say R is the radius of one of these differential elements. Depending on which of these differential elements you look at, that radius is going to differ. So that's going to be a variable in the equations we're going to set up in a moment, which is unfortunate because it's going to make an integration we have to do later quite a bit more difficult. Step 2, I want to write an expression for the area of the differential ring, dA, in terms of the thickness of the ring, dr. So we can actually do that based on the 3 variables we have identified. We have dA, we have dC, and we have dr. And I want an expression for what the area of that blue ring would be. Now, if it's easier for you to do, what you can do is you can take the ring and you can kind of like cut it at a point and then just stretch it out to like form a rectangle. This might be easier to visualize in terms of identifying what the area looks like. Not necessary to do though. But let's say we did that. We took that circular ring, we cut it, and then we unfolded it into the shape of a rectangle. So we want to figure out this area dA. And to do that, we need to know what the length of the rectangle is and also what the width is. So the width of the rectangle would just be the differential thickness. So that's dr. And then the length of the rectangle would be the circumference of that ring, which is dC. And I can write dC in terms of dr So circumference of a circle is 2 pi times r. Therefore, we can write down dc as being 2 times pi times r, where r is just the radius of the ring. Therefore, if we calculate dA, so the area of that rectangle will be length times width, you'd have 2 times pi times r times dr. The length is 2 pi r, and the width would be the infinitely small thickness dr, and that's my area equation. dA equals 2 pi r dr. Step 3, we want to get an expression for the charge in one of these differential rings, and we're going to write it in terms of the thickness of the ring, dr. So we're going to have to make use of the surface charge density to do that. And again, there's two ways to set this up. One, we can look at some ratios, or two, you're going to simply write down what the expression is if you think you know what the dq equation is. But I'll show you what the ratio would be. So if we look at the ratio between the total charge in the ring Q compared to the charge in the total charge in the disk Q to the charge in that infinitely small ring dq, that would be the same as the ratio between the total area of the disk compared to the area of the little tiny ring we see there, dA. We want an equation for capital Q, so we manipulate that. No, not a capital Q. We want dq. So if we manipulate for dq, it would be Q divided by A times dA. Q divided by A is defined as my surface charge density. Therefore, I can write down dA. Oh yeah, and also just recalling from the previous slide, dA is 2 pi r times dr. So that equation dA, that's the circumference of the ring multiplied by its thickness. So we'll do two substitutions. We'll replace Q divided by A with sigma, and we'll replace dA with 2 pi r times dr. So if I do that, I would then have an expression for the charge in that infinitely small ring, and that's dq is equal to 2 pi r sigma multiplied by dr. Again, that's the charge in one of those infinitely small rings that makes up the entire disk. Step 4, we want to determine the distance from the differential ring I have, so that's dq, to a point that we're interested in. And again, that point is located at a distance z from the center of the ring along the z-axis. So if we go ahead and draw that distance, so I just chose like some arbitrary point on the differential ring to draw the distance a from. And if we do draw that, then just going to point this out that even though it's tough to see here, this angle between R and Z, that is a right angle. So we do have a right angle triangle that would look like this right here. It's a right angle triangle, just been twisted along the z-axis. So we can write down an equation for A, and A would be the square root of z squared plus r squared using Pythagorean theorem. Step 5, we want to write an expression for the electric potential due to the infinitely small ring of charge dq. So we're going to call that electric potential dV. Again, the great thing about doing these derivations for electric potential is that we do not care about direction, because electric potential is a scalar quantity. If we were dealing with electric field, it would be a lot more complicated, because then we'd have to look at which component of the electric field is actually adding up to the total electric field from the disk. So this derivation is much simpler to do if we just stick to electric potential, because it's a scalar quantity. So our equation for electric potential at a point is V is equal to KQ divided by R. Now, I just want to clarify here. In that equation, R represents the distance from your charge to your point of interest. However, we've already used little r for a variable. So in the setup of the disk, we defined little r as being the distance from the center of the disk to our infinitely small ring. So we've already used that variable up. Therefore, in my electric potential at a point equation, instead of writing down kq over r, I'll write down kq divided by the variable we've identified to be the distance from the ring to point P. That's A. So we can write down V is equal to kq divided by A. But we want to know what the electric potential is just to that single ring of charge. So therefore, we'd have dV is equal to K multiplied by dQ divided by A. We're going to do a couple of substitutions. One, we're going to substitute in that equation for what dQ is that we derived in a previous step. So that's 2 pi r times sigma multiplied by dr. And we're also going to replace the lowercase a, which we got from Pythagorean theorem, and that's a is equal to the square root of z squared plus r squared. So we're going to take both of those and we're going to plug them into the equation for dV. We'll replace dq and we'll replace a. And if I do that, you would then get an equation that looks like dV is equal to 2 times pi times r times sigma times k, all divided by the square root of z squared plus r squared multiplied by dr. And now we're pretty much ready to set up and evaluate the integral to figure out the electric potential from the whole disk. So step 6. So our equation so far is just the electric potential due to a single ring of charge, but we want the electric potential due to the entire disk. So to do it for the entire disk, we have to add every single ring of charge together. So the way we're going to do that is we're going to add every single ring of charge together, and we're going to do it over the entire radius of the disk that we see here. Okay, we'll set the integral up right now, and then we're going to, in the example problem, we're going to solve it. So my lower limit of integration would be where r is equal to 0. Okay, so that's where we're starting at. We're starting at the center of the disk. Okay, so that's where I'd want my first infinitely small ring to be located at. And then my upper limit of integration would be r is equal to capital R. So that's the outer radius of the disk, or just the radius of the disk. And that's where my last infinitely small ring would be located. And by integrating, we're going to add every single infinitely small ring together from r equals 0 to r is equal to capital R. Therefore, my equation would look like V is equal to the integral from 0 to capital R of 2 pi r sigma k divided by z squared plus r squared multiplied by dr. Okay, we're going to evaluate this integral in this example problem now. So let me grab a pen here. Okay, so first things first, if anything's constant, we can pull it out of the integral. So let's identify all of our constants. So we're going to figure out what V is. So the 2 can be pulled out of the integral. The pi can be pulled out of the integral. Now, little r you cannot pull out of the integral because little r is a variable. Okay, little r defines like the distance from the center of the ring to all of your differential elements, but that's going to change from the center of the ring to the outside. So that has to stay inside of the integral. Okay, the surface charge density we can pull out. And then we have Coulomb's constant we can pull out. So then we'd have 0 to r. And then we'd be left with r divided by the square root of z squared plus r squared. And we're going to integrate that with respect to r. Now, there's 2 ways you can do this. So this kind of integral you see here is actually beyond any of the antiderivatives that we'd find on the formula sheet. So we're not going to get any help there. We could look at an integration table just to identify what the antiderivative is, but there is a way we can actually do this using a very clever substitution. Okay, so here's what I'm going to do. First of all, I'm going to take this 2. You'll see why I do this in a moment. So I'm going to take this 2, and I'm going to put it back into the integral. Okay, so it's going to go right here. So let's rewrite the integral out then. So this would then be v is equal to pi times sigma times k. And then we're going to integrate from 0 to r of 2r dr divided by the square root of z squared plus r squared. Now, the way I'm going to solve this integral is I'm going to make a substitution. So I'm going to make a substitution for the denominator, the z squared plus the r squared. So what I'm going to do is I'm going to say let u equal z squared plus r squared. So if we write the integral out, and just for a moment, I'm going to intentionally leave the limits of integration undefined. So then we'd have pi times sigma times k. And then we're going to integrate. I'm also going to leave the top alone for a moment here. But if we replace u with z squared plus r squared with u, we would then have just the square root of u. Now, when you make a substitution like this, you actually have to change the limits of integration as well. So the way to change the top limit of integration is this equation up here. This is actually u as a function of r. So to identify the new limits of integration, you have to take this function and you have to evaluate it at the limits of integration that I see here. So my lower limit of integration would be determined by figuring out u at the lower limit of integration, which is u at 0. Okay, u at 0 would be z squared plus 0 squared. So that would just be equal to z squared. So that's my lower limit of integration, z squared. To get the upper limit of integration, we take this expression for u, and we're going to evaluate it at capital R. So at capital R, this would then be z squared plus r squared. So that's going to be my upper limit of integration, z squared plus capital R squared. Now, the other thing I'm going to do is this equation that I did the substitution for, u, which is equal to z squared plus r squared, I'm going to take the derivative of this with respect to r. So I'm going to figure out du with respect to r. Okay, so the derivative of u with respect to r would be, well, the derivative of z would just be a constant, so we can ignore that. That would just be 0. And the derivative of r squared with respect to r would just be 2r. Okay, so we got 2r here. Now, normally in a substitution like this, what I would do is I would isolate for dr, so like dr, and write it in terms of du, and then plug it into the equation and see what happens. But actually here, if you isolate for du, something a lot more helpful is going to occur. So if I get du isolated, du would be equal to 2r times dr. Now, the reason I want to do that is because if you look back in your integral, so let's highlight this, 2r dr, look, 2r dr is in the numerator here. So I can actually replace the entire numerator with du, okay? So this is a method called substitution to solve this integration. So we actually don't need to go to an integration table to solve this. if you understand like how like the substitution method works. I believe you learned this in your AP calculus course, so you may have some familiarity with that method from there. If not, we'll just kind of like go along with what we've got here. Okay, so I'm going to replace 2r dr with du. So let's go back to my purple felt now. So this would be du. Okay, now we'll do two things here. So I want to write the square root of u as a power. So this would be pi multiplied by sigma multiplied by k, and then the integral from z squared to z squared plus r squared. And then in the denominator, this would be 1 over u to the 1/2. So if I move to the numerator, it'd be u to the negative 1 over 2, and then du. Okay, I feel like I'm running out of space, so I'm just going to rewrite this out on the next slide here, and then we'll actually evaluate the integral. Actually, we can do that in one step, so let's go over here now. Okay, so to evaluate this integral, we would have the stuff on the outside, so that's pi sigma k. And then the antiderivative of u to the negative 1/2 would be, you're going to add 1 to the numerator. We go u to the negative 1/2 plus 1. And then we're going to divide by u to the negative 1/2 plus 1. And we're going to evaluate this from z squared to z squared plus r squared. This antiderivative, by the way, you can get that off of the formula sheet. Okay, so this would then be pi times sigma times k. And then let's clean this up a bit. So this would then turn into u to the positive 1/2 divided by 1/2. And we're going to evaluate this from z squared to z squared plus r squared. Okay, the 1/2 can be pulled out here. So we can pull this 1/2 out. And because we're dividing by 1/2, 1 divided by 1/2 is actually going to turn that into a 2. So this would then be equal to 2, and then pi sigma k. And then we would have, okay, let's plug this in. So z squared plus r squared to the power of 1/2, and then subtract z squared z squared to the power of 1/2. And we're pretty much done here. So now my equation would be 2 times pi times sigma times k, and then multiply by, instead of writing down the 1/2, let's turn it into a square root. So this would be the square root of z squared plus r squared. And then the square root of z squared would just be z. So this would just be subtract z, and that's my equation for the electric potential. Now, if you did want to figure out what the electric field was at this position Z, I think the easiest thing to do, instead of like setting up a complicated integral, because electric field's tough to set up because you have to worry about the components of the electric field. Once you have an equation for the electric potential, you can actually just take the derivative of the electric potential with respect to your variable, which I think in this situation would be Z, and then that would allow you to figure out what the electric field is. I think that would be a lot easier in comparison to trying to set up the electric field integral on your own. And I believe in the uh, problem, the assignment section of electric potential on the axis of a disk, and assignment number 8, I think I asked you to do that, to figure out what is the electric field by taking the derivative of that equation. Okay, so that's it for kind of like the first 5 lessons dealt with these continuous charge distributions for various objects. And then in the last 2 lessons, we're going to shift focus to magnetism and look at some continuous current distributions. And I'll talk to you then.